energy harvesting technology for self-powered electronic systems, MEMS and nanotechnologies, and flexible electronics. So this is my presentation layout. I'm going to introduce two of my research works based on advanced materials. The first one is self-powered sensing device based on hydrogel material. And the second one is a flexible electronic device based on liquid metal. And finally, I'm going to talk about my current and future works. Okay, the first one is self-powered sensing device based on hydrogel material. So as far as we know, in recent years, as the rapid development of wireless sensor networks and wearable electronics, actually we have more requirements on energy. So we need to often change the batteries for the sensors and for the electronic devices. But the problem is that, like the wireless sensor network, one network can contain more than hundreds of sensors. It's really inconvenient to change the batteries one by one because battery's power is limited. And also it will cause very high maintenance fee. And thirdly, the batteries also can cause the environment contamination. So based on the above considerations, researchers developed the energy harvesting technologies. So that is, we can collect the environmental energy such as the solar, thermal, wind, or vibration energies and convert it into electricity and power the sensors or wearable electronics. So no need to use any batteries. Then we can provide unlimited power. Also, it's eco-friendly. It's a kind of green energy technology. So recent years, we have a lot of materials to generate power, such as piezoelectric materials or thermoelectric materials. We can convert the environmental energy into electricity. But we still hope we can develop more advanced materials which can generate power. So, for example, in some special applications like for biomedical applications, sometimes we need to implant a sensor into the patient's body. But if later there's no power, we need to change the battery, even we need to do the surgery again. So that can be very painful and also inconvenient to the patient. So we also hope we can find some biocompatible material which can generate electricity and power the sensors. So hydrogel is one material which is used in biomedical applications a lot. It has many advantages such as great biocompatibility, it's safe to human body, and it's also flexible and elastic. It can endure vibrations with much higher frequency. So we think about how about to use hydrogel to be the main power generation material. So based on this idea, we proposed one concept to generate electricity based on hydrogel material. We can see this is the working principle schematic. So there are two conductive plates, and there's one dielectric layer. We put one hemisphere-shaped hydrogel inside or between them. Then we found that when the environment there is vibrations, upper and down shaking, because of the contact area changing, then there's non-equilibrium of the charge the charge distribution is changing. So because of it, the electrons, they must transfer from bottom side to upper side to keep the balance. And when the plate is coming down, the electrons also must come down again. So based on this phenomenon, there's current flow through the outside circuit. Then we can convert outside the environment vibrations into electricity. So this is our design concept based on non-equilibrium of the charge. So we fabricate the hydrogel hemispheres. So firstly, we used the 3D printing technology to fabricate the wood and get the hydrogel hemispheres. Then we established the experiment testing system. So we placed the hydrogel-based energy harvester on the shaker and used the oscilloscope to monitor its output. So through the results, we found that when there's a vibration from the environment, the hydrogel-based energy harvester can generate the power. So this is the output voltage waveform. And we also compared it with the water droplet-based energy harvester, which is proposed in the reference paper. We found that the hydrogel-based energy harvester can get wider bandwidth. It means we know in the environment, the vibration frequency is often changing. Normally, it's not stable. So we also hope the device, the energy harvesters, can collect the power and transfer it into electricity steadily. So no matter how much changing of the frequency, but it always can collect the vibration energy and convert it into electricity. So wide bandwidth is very important. So hydrogel-based energy harvester can have wider bandwidth, and also it shows higher output performance than water droplet-based energy harvester. But we found one hemisphere hydrogel, the power is still not enough yet. So the output voltage is about 100 millivolts. So how to further increase the power? So that is the question. Then we think about how about to use the array configuration. Then we increase the number of hydrogel hemispheres. And we found that as the increasing of the number of hydrogels, the output power, output voltage is also increased. So even can be more than 0.6 volts. And it can be directly used to operate an LCD screen. We can see the video. So with 1 Hz sine wave and 2 Hz sine wave vibrations, and even increase to 40 Hz. And return back to 2 Hz again. So we can see it can directly operate one LCD screen, and we also tested the output voltage waveform under different excitations. So sine wave, square wave, and triangular wave, and sawtooth wave. So different excitations, but the hydrogel-based energy harvester shows nice output performance. We also test its output current waveform. So this one is only one hemisphere, and C is 6 hydrogel hemispheres. And we also calculated the charge. And then we did the output performance testament and the impedance matching. We found with the load resistance about 0.1 mega ohm, it can get the peak output power about 1 microwatt. It can power some sensor device or some electronics. So compare with the literatures. So this work shows a wider bandwidth. That is one of important advantages of this design. Wide bandwidth can cover almost all the daily common frequency range, and also it shows nice power output. So based on it, we developed the self-powered vibration sensor. We test the continuous impact and post-impact, and we also put the hydrogel-based energy harvester vibration sensor on the air maker and test the air maker's vibration. We can get. So except it, we also developed the self-powered force sensor based on it. So we can see when we applied different level of force, so little force or a little bit more force and even big force, it can show different patterns. Then we can know the force level. So this is the video. So little force and a little bit more force. Higher force. And big force. Okay. And we also consider about the influence of the hydrogel's shape. So we tried the hemisphere shape and also the cuboid shape. In the test, we found actually the cuboid shape can get higher output voltage, but the problem is that the wave is very narrow. So we compared the energy, and we found hemisphere shape can get higher energy. So that's why finally we choose this shape. Okay, my second research work is flexible electronic device based on liquid metal. So when we talk about liquid metal, what's your imagination about liquid metal? Have you ever watched the movie Terminator? So I still remember when I was a child, I watched that movie, the liquid metal robot. It was so much impressive for me. It almost became one of my nightmares when I was a child. I never expected when I grow up, I even need to do research which is related on liquid metal. Fortunately, the real liquid metal seems not so much scared as it is in the movie. Okay, we can talk about the flexible and stretchable electronics based on liquid metal. So there's a definition about flexible and stretchable electronics. So actually nowadays, because of the development of wearable electronics, and we also hope we can develop some soft, flexible screen like the phone's display or computer display. We hope it can be bended or folded or even stretchable. So, but the problem is that if we use the conventional metal like a gold to make the circuit line, the problem is that once we bend it or twist it or even stretch it, the line will be broken. So the circuit will be disconnected, no more can be used. So that's the problem. So that's why we hope we can develop some flexible and stretchable electronics based on liquid metal. Even we can stretch it, but it can still keep connection. So we compared the different materials. We found that liquid metal has very great conductivity as well as great stretchable ability. So in our daily life, a common liquid metal is mercury. But the problem is that mercury is toxic. It's very dangerous for researchers. So that's why we cannot use it. We need to find another liquid metal instead of mercury. Then we find gallium-based liquid metal. So the gallium-based liquid metal, one of the typical one is the Galinstan. So it mainly compensated by gallium, indium, and tin. So this kind of liquid metal, it can keep the liquid phase even in room temperature. So nowadays, there are different fabrication methods to get liquid metal-based stretchable interconnectors, such as direct writing or injecting. But the existing problem is that first one is the resolution. The resolution is still not high enough. We hope can get a higher resolution. And also sometimes there's the roughness surface. So we found a new wetting behavior of Galinstan on different substrates. So for the Galinstan, one of the drawback is that in the air it's easily be oxidized. So when it's oxidized, it shows some solid phase. So that's why we use HCl acid to remove the oxidation layer. Then it can become liquid phase again. So we can see the reduced Galinstan shows very great hydrophobic behavior on PDMS substrate. But on copper and gold and zinc, Galinstan shows very nice hydrophilic behavior. But we hope if we use it to fabricate some circuit, like the zinc, this one is too much hydrophilic. So finally we choose copper or gold is better. It can still keep the liquid fluid characteristics. So this is our selective liquid metal plating process we proposed. So first we coat PDMS solution on the silicon wafer. After curing, and we cover the gold layer. And through the lithography, we can get the pattern or the circuit. Then we cover the HCl treated liquid metal and rolling on it and remove the extra liquid metal. Then finally, we can find the liquid metal already covered on the pattern. Then after curing and remove the silicon wafer, Finally, we got the flexible device, which can be bended and twisted. So based on this technology, we fabricate complex patterns, such as the square shape, the lines, and even the Chinese words. And we fabricate different patterns based on liquid metal or PDMS substrate. It can be stretched and it's flexible. So we compare it with the traditional line, so like the gold line in the circuit. So when it is stretched 100%, it's already broken, disconnected. Even when we return it back, but it's still broken and disconnected. That is the problem. And we also fabricate the liquid metal lines on PDMS substrate, and we stretch it about 100% and return it back. Then we found even we stretch it and return it back, it always keep connection. Even the resistance, there's not big changing of the resistance. So this width is about 10 micrometers width, and this one is about 50 micrometers width. So we put one LED here and the two liquid metal lines. We found it bending, twisting, and stretching 60%, but it's always keep connection and the LED is working. And we also compared with the, we tested the VI, the curve. We can calculate the resistance. We found that even we bend it, twist it, and stretch it, the resistance, there's almost no change. Always can keep stable resistance. That is very important. Even we twist it plus stretch it together, also more than 6,000 cycles, and still keep very good connection. And another merit is that it also has the self-healing ability. So we fabricate the more complicated line, the Galinstan circuit, and placed one LED. We found even we twist it, bend it, and stretch it, it always keep connection and working. Even we use knife to cut it. And after cutting and we put it back, it is still reconnecting and can still work. So that is very important because the liquid metal has the liquid phase. So even we cut it and reconnect it, then it can still keep connection. We call it self-healing ability. And we also test the resistance changing, bending, twisting, stretching, even reconnection. Almost there's no changing of resistance. And also more than 2,000 cycles. So based on this technology, we developed the flexible and the stretchable pulse sensor. So we can see the pulse sensor can be bended and twisted and can test our body's pulse. So like this way, this is the system. So we put the sensor on our fingers, then on the computer, it can show our heart beating frequency. So finally, we realized that the flexible and stretchable pulse sensor based on this liquid and metal. So I'm going to talk about my current and future works. The first one is self-powered biomedical sensor. So to check the toxicity of new developed medicine. And second one is the artificial skin for robot. So like some dangerous situation, like we in front of the fire or the coronavirus, we can use the robot to instead of the firemen and or doctors and nurse. Then we can save a lot of people's life. So the artificial skin. And third one is the self-powered stretchable sensor. So for like the wearable electronics using and so on.